In the last slide, we mentioned that I mentioned that we were going to talk about some of the factors that lead us to believe the mechanism extremes. And so one of these has to do with nucleophilicity. Nucleophilicity is a kinetic property. It has to do with rates, how fast a reaction occurs. And so typically these are measured against standard compounds. This is one of them, bromoethane and ammonia reaction to do a substitution to make the ammonium product. And so we look at different nucleophiles to see how fast they do the reaction, and we measure their rates of reaction. And nucleophilicity is a measure of how strong a nucleophile is, how fast the reaction is with that nucleophile. So on the next slide, we have some nucleophiles that the text gives us. I have a couple extra that are big and bold in the good section. And so the good nucleophiles are halides, bromide, and iodide. Sulfur anions are good nucleophiles. Oxygen anions are generally good nucleophiles, except in the case of where the R group is very sterically bulky, like a tert-butyl group. Then the O minus is with the tert-butyl group is called a tert-butoxy. That's not a good nucleophile because it's too sterically hindered. That is, the transition state energy is very high because of steric crowding. But we'll talk about that a little bit later. Suffice to say, oxygen minuses and sulfur minuses are good nucleophiles. The cyanide is a good nucleophile that I've added, and so is the acetylide. That's the anion of an alkyne. Those are good nucleophiles. Those are accessible because we could take the proton off a tertiary terminal alkyne in order to make that carbanion. And azides are good nucleophiles. These are ones that you're going to see. So the moderate nucleophiles are the ones in the middle. These are chloride and fluoride, and the oxygen of acetate or other carboxylates. Those are the first ones. And neutral sulfurs are not such good nucleophiles, and neutral nitrogens are not such good nucleophiles. And then the poor nucleophiles are the ones with no charge. Notice that poor nucleophiles, no charge. This is generally true. Some nucleophiles are better than others. I'll mention a couple of things about that I'd like you to know. That's mainly encapsulated in the comment that I have in red below. Generally, the more basic the anion, the stronger it is as a nucleophile. And so that means it reacts faster. Keep in mind, if it's a strong base, then it wants a positive charge fairly badly. Remember, a strong base wants a proton very badly. So a strong base wants a positive charge very badly. And so there's a correlation between strong bases and strong nucleophiles, that is, good nucleophiles. If it is a strong base, it wants to donate its electrons to a positive charge. That's exactly what nucleophiles do. So good nucleophiles are typically strong bases, and that's one thing to recognize. Another thing is that typically, all the other things being equal, for example, everything having a negative charge, that as you go to the right on the periodic table, for example, from carbon to nitrogen to oxygen to fluorine, as you go to the right, those are weaker nucleophiles. Why is that so? Well, fluoride is very electronegative. It holds on to its electrons very tightly. It doesn't share them very well. And it's fairly stable as an anion. That's one of the markers of not sharing the electrons well. So in any case, for all of those anions, as you go to the right on the periodic table, you get stronger nucleophiles. Also, generally, as you go down a column in the periodic table, you get better nucleophiles. And so this is not entirely true. There have been a whole lot of studies with different electrophiles and different solvents to see how these effects are. I'll talk a little bit more about better nucleophiles going down a column of the periodic table a little bit later. But for now, just accept that other things being equal, as you go to the right in the periodic table, you'll get stronger nucleophiles. And as you go down the periodic table, you'll get stronger nucleophiles as well. So what about the structure of the haloalkane? How does that influence the reaction? So for SN1 reactions, you essentially want tertiary is the best. Secondary are okay for SN1 reactions. These are the unimolecular. These are the ones that have the carbocation intermediate. Primary and methyl electrophiles are terrible, and so they should not even be in there. But their rates are extremely slow, and so they are slower than secondary and tertiary. So the reason for this is that generally SN1 reactions are governed by electronic factors, and specifically, what is the stability of the intermediate? Remember, the first thing that happens in an SN1 reaction is that you lose a halide and become a carbocation. And so if the carbocation is very high in energy, then it's very hard to lose the halide to become the carbocation, and so those are not favored reactions. And so for SN1 reactions, you should think about tertiary. You should also think about resonance stabilized carbocations. If they're resonance stabilized, they're going to be much better than carbocations that are not resonance stabilized, and we'll see examples of these. For SN2 reactions, you don't make a carbocation, so you don't have to worry about the stability of the carbocation. Recall in an SN2 reaction, the halide is leaving at the same time the nucleophile is coming in. In a way, you can think about the nucleophile coming in helping to push out the halide. And so what do you want to be able to do? Well, you want the nucleophile to come in fairly easily. And so you want less sterically hindered R groups, that is the electrophilic carbon. You want those to be less sterically hindered. Methyl is the least sterically hindered among these. And then primary alkyl halides are, they have one R group and two hydrogens on a primary carbon, a primary alkyl halide. So those are faster. And so methyl halides and primary alkyl halides, those are the ones that are good for SN2 reactions. Secondary can work with SN1 or SN2, and you're going to have to look a little bit more closely at the rest of the conditions for a secondary alkyl halide. So what are the reasons why for SN2 reactions steric interactions are so important? So on the left is a primary alkyl halide, this is bromoethane, and on the right is the tert-butyl bromide, which is a tertiary alkyl halide. And so the nucleophile has to come in. It has to come in from in back of the carbon-bromine bond if it's an SN2 reaction in either case. It doesn't have a heck of a lot of problem to come in with a bromoethane. There's only one methyl group there, and so it can squeeze in fairly easily. However, if it's the tert-butyl group that the bromine is attached to, then those methyl groups make it very hard for the nucleophile to come in. Essentially, if we drew the transition state of that reaction, we'd say there's a lot of steric congestion in the transition state. That makes the energy of the transition state very high. If the energy of the transition state is very high, then the activation barrier is very high, so the reaction is very slow. And so that's the real way that you should think about this. But it's okay for you to think about it's crowded for the nucleophile to come in with a tertiary alkyl group on the alkyl halide. And so for SN1 reactions, these are carbocation stability is the major issue for us. Tertiary alkyl halide never occurs by rather a primary alkyl halide or a methyl halide never occur by SN1 reactions. And in contrast, for SN2 reactions, those are governed by steric factors. How big are the groups around the carbon that bears the halogen, that's the leaving group. And the bigger the group, the slower the reaction, or the more groups, the slower the reaction. And so tertiary alkyl halides never go by SN2 reaction. Secondary are in between. Again, you have to look a little more closely at the conditions. What about leaving groups? Well, the best leaving groups is halides, and that's what this whole chapter is about. Iodide, bromide, and chloride are the best ones. The carbon-fluorine bond is fairly strong, and so that's a hard one to leave. If you have a fairly strong bond, that means that the stability of that bond is very high, and so it doesn't want to break because it's got a lot of stability. So those are the relative reactivities of the alkyl iodides, alkyl bromides, alkyl chlorides. Notice water can be a good leaving group. That's somewhere around as good as having a chloride. The other ones are not so good at all, so you should think about those not occurring by this mechanism. And so we'll ignore those. Water can be a good leaving group, and that was shown in the last slide. How do we make water a good leaving group? Well, let's look at the situation where water is not a good leaving group, and this is a tertiary alcohol, for example. We would have to, if this is tertiary, so we're going to say this is an SN1 reaction. the OH would have to leave as OH minus, and at the end of that process of the OH leaving, the hydroxy leaving, we're going to have a carbocation with hydroxide minus, and that's not going to occur because hydroxide is not a stable anion and so it's not a good leaving group. It's also a pretty strong carbon-oxygen bond. That doesn't occur. However, if first we protonate the hydroxy group, then we have a protonated alcohol product, and that protonated alcohol essentially has a water attached to the tertiary carbon. And if that water leaves, water is a good leaving group. A measure of how good a leaving group is, or one way you should think about it, is if it's very stable after it left, it's a good leaving group. Is water stable? We hope so, otherwise we'd all explode, and that would not be too comfortable. But in any case, water is a very good leaving group because it's stable. We get the carbocation after water leaves, and chloride could come in and make a new bond, and so we get the tertiary alkyl halide from this reaction. So in any case, the take-home message here is water is not a good, rather hydroxide is not a good leaving group. But if we, under acidic conditions, if we can protonate the alcohol, then we can make water, which is a good leaving group, and then the nucleophile can come in to make a new bond. By the way, that reaction at the bottom is an acid-base reaction, and I want you to, the first step of that, I want you to think about what the acid-base reaction is between, not even think about it, I want you to analyze it between that tertiary alcohol and HCl. Draw that as an equilibrium and figure out which is the favored side, whether it's favored to have the hydroxy in the HCl or it's favored to have the protonated alcohol in the chloride. So protic solvents, these are solvents that are good for SN1 reactions. The reason they're good for SN1 reactions is because SN1 reactions have a carbocation. That carbocation can be stabilized by the donation of electron pairs from the solvents. So the carbocation is a very polar intermediate that's stabilized by very polar solvents, and the most polar of the solvents are these polar protic solvents. So for SN1 reactions, you prefer polar protic solvents, like the ones that are shown: water, formic acid, methanol, ethanol, and acetic acid. For SN2 reactions, we'd rather have aprotic solvents, and the kind of aprotic solvents actually we need are polar aprotic. The reason we want polar is that if you think about the transition state, there's charge being developed in the transition state. The nucleophile, for example, begins to come in with a negative charge, and in the transition state, it's got a partial negative charge, the nucleophile does, because it's partly bonding. And the leaving group is leaving, for example, a chloride, and it's got a partial negative charge as it's leaving. And so what you need to stabilize the transition state is a polar solvent. And so these are all polar solvents that stabilize transition states. In this particular case, you don't want a polar protic solvent, because the protic solvent can interact, the protons of the protic solvent can interact with the negative charge of the nucleophile. And so if these surround the nucleophile, it makes the nucleophile have a harder time to get into the electrophile to make the new bond. Another way to say that is that having protons from protic solvents around the nucleophile puts a shell around the nucleophile so that it's harder to react. And so you want polar aprotic solvents for SN2 reactions. So here's a table that summarizes all this that I talked about before. For methyl halides, SN2 is favored, SN1 doesn't occur. For primary alkyl halides, SN2 is favored, SN1 does not occur. Secondary alkyl halides could go SN2 or could go SN1. So the text tells you, or rather this slide presentation tells you, for SN2 reactions to be favored, polar aprotic solvents. For SN1 reactions to be favored, polar protic solvents. I'll add something to this, that if there's something else there that stabilizes the carbocation, such as resonance, maybe we have a phenyl or a vinyl group attached to the carbocation that can stabilize the carbocation by resonance, then we should guess for secondary alkyl halides SN1. So tertiary alkyl halides, no SN2, only SN1. And as far as the product that you get, if you're losing the halide in an SN2 reaction, if you're substituting it for a nucleophile, then you'll, and if that's a stereocenter, then you'll have inversion of configuration. If you're losing the halide in an SN1 reaction at the stereocenter, that's going to give you racemization, and you have to automatically consider those as you're writing out your reaction product. So why inversion for SN2? I put this slide together, so hopefully this will give you a good clue, better clue as to what's going on. We did talk about this a little earlier, but I did want to emphasize this for SN2 reactions. So this is a secondary alkyl halide that I'm showing you up there. That'll do either SN1 or SN2. Let's assume these are polar aprotic conditions. So these are SN2 conditions. The nucleophile comes into the smaller lobe at the backside of the carbon-halogen bond. In the transition state, we've half broken the carbon-halogen bond, and we've half made the carbon azide bond. And so there's a negative charge that's building up on the N3 minus. The bromide is also building up charge as it's leaving, so that's delta minus. That's what the transition state looks like. Notice, by the way, in that transition state, the methyl group and the hydrogen and the ethyl that are attached to the carbon stereocenter, they're all migrating to the right. They're flipping like like an umbrella in the wind, and they're migrating to the right side of that carbon as we make the new carbon-nitrogen bond. They're inverting. And so if we analyze the stereochemistry of the product, before we do that, we need to remember that we get a bromide at the end of all of this process. Lots of times we forget about those. As organic chemists, we're much more concerned about the organic part of this reaction, but we should remember them. If we analyze the stereochemistry of the products, it's R for the starting material and it's S for the product. And so we've gone from R to S. This is inversion. I'm going to say this, in this class you will never see an SN2 reaction at a stereocenter like this where you start with R and end with R. You can do that and still have inversion. For all the cases you'll see here, we're going to go from R to S or S to R if it's an SN2 reaction at a stereocenter. And that's what you should be remembering.